In the last lecture, we have discussed two problems or two issues which need to be taken care of in the numerical simulation of spherically symmetric perturbations, unstable spherically symmetric perturbations, which is the initial condition. Well, we don't want to kick our star or to initiate the pulsation by an external perturbation, because otherwise we would not know whether we are simulating the evolution of an external perturbation or an intrinsic instability. And the second, and on the other hand, there are intrinsic perturbations once the numerical scheme is not compatible or not identical with the scheme by which the hydrostatic model was constructed, and in that case we need an initial relaxation to hydrostatic equilibrium to avoid initial perturbation and to allow the evolution to proceed through the linear regime of exponential growth. And the much more important is the energy balance. We have seen that in the simulation, the various energies appearing in the energy balance differ by many orders of magnitude. And in order to determine the smallest energy terms in the energy balance, we need an accuracy of better than 10 to minus 5, which cannot be achieved by simply refining the grid or refining the discretion of the time of the time evolution. Okay, so let us describe how we never, despite of these problems, how we have to formulate or how we have to design the numerical scheme to match these extreme accuracy requirements. I've shown that it's actually possible to reach this accuracy and to generate meaningful simulations, but the question is what do we have to do? How do we have to design the numerical scheme to reach these accuracies? Well, first of all, I have to show you the equations which have been solved for the evolution of an instability into the nonlinear regime. We adopt the Lagrangian description as always for one-dimensional configuration. And in the Lagrangian description, mass conservation, you already know the equation. It's a little bit reformulated compared to the original version. D by dt of 1 over rho is d by dmr of the 4 pi r squared v, which is the divergence, the Lagrangian form of the divergence of the velocity field. Then we have momentum conservation. The acceleration is given by the difference of the pressure gradient and the gravity. There is a term lambda q, which is introduced to avoid difficulties once we have a shock wave appearing. Shock waves cannot be represented by a ordinary numerical scheme. It involves discontinuities, and what you have to do is to smear out these discontinuities to represent them numerically. So in order to do this, we have to introduce artificial viscosity, and this term is meant to describe the artificial viscosity needed to resolve discontinuities, in particular shock waves. Okay, then we have the energy equations. This energy equation, this is the change of energy with respect, internal energy with respect to time, which is given by a term P times divergence, pressure times divergence of the velocity field. This is the PDV work. And then we have the divergence of the flux, which is splitted here into two parts, into the divergence of the radiative and the convective flux. The convective flux, or the convective luminosity, the perturbation of the convective luminosity, is set to 0 according to the frozen-in approximation. And once we introduce a viscosity term in the momentum equation, then a corresponding term will appear in the energy equation, because through these artificial viscosity terms, energy is transferred from the mechanical part into the thermal part of the energy. Okay. Well, the epsilon terms have been omitted because we do not consider the nuclearly active regions in the star. Then we have the energy transport, and we write it in terms of the gradient of the radiation pressure. The radially transported part of the energy flux is given by the gradient of the radiation pressure times the diffusion constant involving the opacity kappa. Well, and finally, of course, this is the acceleration, which is given by the first time derivative of the velocity. Of course, in the Lagrangian scheme, we have to add the definition of the velocity, which is simply the derivative of the position vector with respect to time. So this is given by the velocity. So this is the system of equation which is solved numerically. To remind you what I've said, no nuclear energy generation, constant convective flux, frozen in approximation, radiation transport, optically thick part is considered only, lambda q and mu q denote the artificial viscosity necessary for the treatment of shock waves, and finally the variables which we have used for the integration, for the numerical integration here, are the density, pressure, and the radiation pressure instead of the temperature. Radiation pressure is given by T24, so we can equivalently take the radiation pressure as a variable instead of the temperature, internal energy, radiative flux, convective flux, radius, position vector, and the velocity. Okay, what we would like to, how do we do the discretization? The independent variable is the mass coordinate mr, and we use a so-called staggered mesh, where all the vector valued quantities are defined on the grid points and the scalar quantities are defined on the cells between two grid points. Vector variables like radius, velocity, radiative flux are defined on the nodes or on the grid points, whereas the scalar variables density, pressure, and the radiation pressure and internal density are defined in the cells. How does it look like? Well, to show you the way how discretization is done in the spatial variables. So we have the mass is the independent variables, and we have M1 and M2 denotes the mass of the cell. So these are scalar, in that sense, scalar quantities, and differentiation with respect to the MIs are done with taking the differences of the masses of neighboring cells or neighboring nodes. Well, we can also define masses apart from defining the masses within the computation cell. We can define the masses on the nodes or on the grid points by taking the arithmetic average of the masses of two neighboring cells. So the mass mi over bar is simply the arithmetic mean of the masses of the two neighboring cells. So we can either define the gradients by the difference of the masses of two neighboring cells or the masses of two neighboring nodes. Okay, that's for the spatial discretization, and now we come to the time differentiation. Time differentiation is done in the following way. Well, we have two consecutive time steps, Tn plus 1 and Tn. These are two consecutive time steps. Their difference is two different times, not time steps, two different times at which the solution is to be evaluated, and the difference of these times is the time step tau. Once we have a quantity which is to be differentiated with respect to time, then we can take q hat. Q hat is the quantity q at time tn plus 1. Subtract the value of the quantity at time tn and divide it by the time step tau. So the difference at two consecutive times, the difference of the quantity at the new time step and the old time step divided by the difference of the new time and the old time. So this is the simplest way to represent the time derivative of a quantity in terms or in a numerical way. Replace the differentials by a difference scheme. So the differentials are replaced by differences. Okay, well, in the following we will introduce so-called time averages of a quantity. So Q alpha, this is the average, the time average of Q with index alpha is defined as alpha times the quantity at time tn plus 1 plus 1 minus alpha, the quantity at time tn. What does it mean? It means Q can be changed between its value at time tn and time tn plus 1. If alpha is equal to 1, then this is 0, and Q with weight alpha equals 1 is simply the quantity at the new time step at tn plus 1. If alpha is equal to 0, then Q0 would be the quantity at time tn. Okay, so by changing alpha between 0 and 1, we can change the quantity or the evaluation of the quantity between time step tn and tn plus 1. Alpha equals 1 means at the new time step, and alpha equals 0 means Q at the old time step. Why is that important? Well, what we want to have in one of the characteristics of our scheme should be that we would have, or what we would like is to have energy conservation intrinsically built into our system. So one aspect of the energy conservation or the energy balance is, well, once we multiply for instance, our momentum equation with the velocity, and we have a term going velocity times the derivative of velocity, then this should be the derivative of 1/2 v squared. So what we do, we have v times dv by dt. This is, for instance, in the momentum equation. Momentum equation is multiplied with velocity, and we have multiplication of velocity times the acceleration. And what we would like to have, well, this is according to the rules of differentiation. This is d by dt 1/2 v squared. That is necessary to derive or to have energy conservation, because this is replaced by dt of 1/2 v squared. Once we transform or translate this into a difference scheme, this relation is no longer valid. And what we want to have is that within the difference scheme, we have the same properties of the difference scheme as the differential properties. This is a property of the differential operator d by dt, and what we would like to have is that our difference scheme of this relation has the same properties, such that we multiply in the difference scheme v with the derivative of dv by dt. We obtain that this is then within the difference scheme d by dt of 1/2 v squared. Okay, so to illustrate what needs to be done. So the dv by dt is, let's go to the, so let's consider now dr by dt, the derivative of the radius with respect to time, is the velocity. So we say, well, r hat, the definition of the time derivative is r hat minus r, radius vector at the new time step, minus the radius vector of the old time step, divided by the time step is given by the velocity. But which velocity do we have insert on the right hand side? Do we have to insert velocity at time step tn or the velocity at time step tn plus 1? We are free to do it, because the difference scheme does not tell us which velocity or which weight of the velocity has to be inserted here. So the question is, what is the appropriate weight of the velocity which we should set in here? We could have within the original definition of the weight, we could have any weight or any time average of the velocity with alpha between 0 and 1. The question is, which one do we have to insert once we require that within our difference scheme also this relation is valid, which we need for the energy conservation. Okay. So let's consider, well, we have, let's do it on the blackboard, it's perhaps better. So we have v times dv by dt. dv by dt is by definition v hat minus v over, so here we have a question mark. The dv by dt is given by v hat minus v over tau. Well, this has to be the time derivative of 1/2 v squared, and this of course is given by 1/2 times, by definition, v hat squared minus v squared over tau. So the d by dt of 1/2 v squared, we are fixed by definition of this time derivative by v hat squared minus v squared over tau. dv by dt is also fixed. This is v hat minus v, but we don't know how to, with which weight we have to multiply this equation to obtain this as a result. Okay, so we need that v something times v hat minus v is v hat squared minus 1/2 v hat squared minus v squared. So an idea what might be the solution of the problem? Well, if we take, we need this factor 1/2 here. So, well, v hat plus v times v hat minus v is v hat squared minus v squared. So, well, if we take 1/2 v hat plus v times v hat minus v, then we end up with this formula. That's what we wanted to have. This is required, and this v question mark times v hat minus v should give the right hand side. So the quantity which we have to insert here is 1/2 times v hat plus v, which is v with, in terms of the time average, this is v 1/2. v 1/2 is 1/2 of the, it's just in the middle between the old and new time steps, velocity defined in between the old and new time step. So in order to have this relation, which is required once we want to have energy conservation, then we would have to insert here the weight 1/2 or 0.5 for multiplying the velocity. So we have, as a result, we have to insert here on the right hand side v with the weight 1/2. This is required by by asking for the property of the difference scheme to be the same as the differential operator. And once we ask once we require the difference scheme to have this property, then it has the same property as the differential operator, and then we will guarantee that the energy conservation law or energy balance will be satisfied intrinsically. If we take another weight, energy conservation cannot be guaranteed. That's what is meant with a fully conservative scheme. Okay, now we have the second equation, which is, let's consider only the gravitational force here. How do we have to discretize the gravitational force? Well, dv by dt, the acceleration is given by minus gm over r squared, transformed transformed into difference scheme. This is v hat minus v, this is over tau, this is the definition of dv by dt, is equal to minus gmr over r squared. But what is the correct weight, or what is the correct, how does the weighting of r squared to be done in order to guarantee energy conservation? Okay, let's go and consider what is going on what we need for the gravitational force. Well, we multiply to obtain the energy conservation or energy balance. We multiply the force with the velocity. Velocity times the force, of course, concerning the differential properties. This is d by dt of the gravitational potential, because d by dt of gravitational potential gives minus gm over r squared times dr by dt, that is v. So in a differential form, we write this as d by dt of gmr over r. Now, the right-hand side, the discretization of the right-hand side by definition of the time derivative is 1 over tau gm over r hat at the new time step minus gmr over r. Okay, we know that we have, for the velocity, we have to take the weight 1/2. So v has to be taken in the middle between the old and new time step, and we don't know how this quantity has to be discretized, or what is the correct weight for gm over r squared, or the correct weight of 1 over r squared. Now, if we evaluate this term, then we have gm over r hat times r minus r hat over tau. Just rearranging these two terms, we get r minus r hat over tau times gmr over r hat times r. Okay, so this means this r minus r hat over tau is, according to our previous well, we have found out in this equation v has to be inserted with weight 1/2. So v 1/2 is r hat minus r. So we have here we replace r minus r hat over tau by minus v 1/2 times gmr over r hat times r. Now we compare these two expressions, and now we know, well, once we require the difference scheme to have the same property as the differential scheme, as the differentials, namely this equation, then we have to write the gm over r squared as this term and this term. This has to be written as gmr over r hat times r. So taking the new, the r squared has to be replaced by the value of the position vector at the new time times the position vector at the old time. That's something you would not have expected a priori from the beginning. This is the correct, this is the discretization needed to guarantee conservativity of the scheme, to guarantee the validity of the energy conservation intrinsically. That's the way how it needs to be discretized. These are two examples how to derive the correct or a different scheme which intrinsically guarantees energy conservation, or which allows for the energy conservation. Okay, so as a result, velocity has to be taken with the time average 0.5, and the gravitational force has to be taken as gm over r times the gm over radius at the old time and radius at the new time. This is an example, or one of the example, how to discretize and what conservativity, how to discretize the scheme correctly with respect to energy balance, and how to derive a conservative scheme, at least the parts of the conservative scheme. We could now go on and ask what is needed, or how do we have to define the other differentials and the other weights, other time averages for conservativity. Just done for the example of the time derivatives v times dv by dt leading to d by dt 1/2 v squared. Okay. So, well, if we perform the construction of the scheme in that way, then we have intrinsic conservation of energy, and the energy balance will be satisfied intrinsically. Then we end up with a strictly conservative numerical scheme with those fixed time averages. What does it mean? Well, once we consider this, the right-hand side of the differential equation, once the gravity has to be discretized like gm over r hat, this means that the right-hand side of the differential of the original differential equations will contain, here the right-hand side will contain not only quantities at the current time step, but also quantities at the subsequent time step. And this is called a scheme which is implicit with respect to time, because in that case you have to solve an implicit algebraic equation. This is a bit more complicated than an explicit numerical scheme, but let's comment on, or let's consider what an explicit and an implicit scheme with respect to time really is. Okay? So, well, numerical scheme is necessarily implicit with respect to time and requires a solution of an implicit algebraic equation. Okay, what is an implicit or an explicit scheme? Consider you have a differential system here, an ordinary differential system. Du, a vector u, is to be differentiated with respect to time, and the right-hand side is a function of the vector itself and time t. Well, you discretize this in the form as before. The du by dt is u at u hat, which is the value of the vector u at new time step, minus u0, which is the value at the current time step, divided by the difference of the times tn plus 1 plus tn, which is the time step tau. Well, if we assume, or we can assume, that the right-hand side f has to be taken only at the old time step, at the time step where we already know the vector u. U hat is not known, u0 is known. This is the value of the vector at the current time step. Then this is called an explicit scheme, because then we can solve the equation explicitly for the value of the vector u at the new time step. So u is given by u0 plus time step times the value of the function f at the old time step. Everything on the right hand side is known, and the function u hat at meaning the vector at the new time step can be explicitly expressed in terms of the quantities at the old time step Tn. Now, if we have, contrary to the explicit scheme, once we have an implicit scheme, then the function on the right-hand side does not only depend on the values of the vector at the old time step, but also on the new time step. Okay, if you have such an equation, then you have to solve an implicit equation with respect to the values of the vector u at the new time step by an algebraic equation. So you write u hat is u naught plus tau times f plus f, now also depending on the value of the new time, and you have to solve the equation for the values of u, the vector u at the new time. You need an initial guess for the iteration, or for looking for the zeros of this equation. You need an initial value for the iteration, which can be obtained by extrapolation of the solution, but otherwise we have to solve it iteratively, for instance, by a Newton-Raphson method. Okay, so it's much more complicated than an explicit scheme, because this requires an iterative solution of an implicit equation for the vector u hat at the new time step. Well, such a case is we have such. This is the case for the system we have found here, because we have the right-hand side, for instance, gm over r squared is not given by gm over r squared, where r denotes only the value of the radius at the old time step, but is given by gm over r times r hat. So it involves also the value of the position r at the new time step. So we have to solve. This is actually an implicit equation. We have to solve an implicit equation for the value, for instance, of r hat at the new time step. This makes it more complicated, but it is required for conservativity. So for conservativity, the equations for the simulation of pulsations necessarily have to be implicit with respect to time, and they have to satisfy the conditions or requirements for conservativity intrinsically built in the numerical scheme, for instance, for discretizing gravitational force, or for discretizing the velocity u. Okay, so is that clear what the difference of implicit and explicit schemes mean? Explicit scheme is much more complicated than an implicit scheme is much more complicated than an explicit scheme, but for conservativity reasons, we have to have a scheme implicit with respect to time. Okay, so that is an example, or to illustrate how the numerics has to be done for a meaningful simulation of stellar pulsations. Okay, well, essentially we would now have finished our lecture, but to present you perhaps an outlook or perspective for the future, one point or one drawback mentioned initially was we would like to do these simulations, which we can do in 1 dimension. We would also like to do it in 3 dimensions. And the big problem actually is a conservative formulation of gravity in 3 dimensions. Some mathematicians in the past have claimed it is not possible to derive or to provide a conservative formulation of gravity in 3 dimensions. Contrary to the thermal part of the equations, without gravity thermal equations, for which many conservative formulations do exist, so far, or up to a few years ago, no conservative formulation of the gravitational potential and the gravitational force was provided. And some mathematicians were very critical and said it will never be possible. Nevertheless, we have tried to do it, and we found a formulation to do to represent, even in 3 dimensions, to represent the gravitational potential in a conservative way. It's rather time-consuming, and it's a lot of mathematics to show that the form of the gravity which we found finally is in fact conservative. That means that we can generate a scheme where the gravitational energy might also be treated in a conservative way. I have given it here on the transparencies, but with respect to the time which is left, we cannot go through that in detail. But if you're interested, you can try to follow the proof of the representation of the 3-dimensional representation of the gravity, which will be given to you. Well, just I would to sketch briefly how this 3-dimensional formulation of gravity can be done, which subsequently might be used for 3-dimensional simulations. I have to tell you, this is work in progress. We have achieved a conservative formulation of gravity in 3Ds, but we have not applied it to a particular system. So this is still work which needs to be done. Perhaps some of you like to participate in this project. Well, this is just an outlook for what needs to be done in the near future, and what in the far future probably will be available, and we can do then we can perform simulations with satisfy the conservativity requirement and the accuracy requirements necessary for stellar pulsation calculations. Just to anticipate, of course the formulation or the conservativity also in 3 dimensions requires an implicit scheme with respect to time. So we have to solve implicit equations for the solution of the problem. Well, how do we proceed? Well, we adopt the Lagrangian prescription. You already know the equations. This is mass conservation. This is momentum equation. This is the energy equation. And now we denote by U, the vector U, the velocity, and epsilon is the internal energy. We have an energy transport according to the diffusion approximation, radiation diffusion, and the potential equation, the equation for the potential is Poisson's equation for the gravitational potential. We have a thermal and a caloric equation state, and we have a prescription for the opacity. Okay, so I only go roughly through the scheme of the derivation. Well, we have to satisfy the energy balance. And let's consider first the differential form, which is known to you already. We multiply the momentum equation with the velocity vector and add the energy integration and integrate over an arbitrary volume. Then we are left with the time derivative of kinetic energy plus internal energy is the term which involves the gravity, rho times velocity times the gradient of the potential, plus or minus the acoustic energy flux. This is the pressure times velocity times the normal vector times the of the surface element and times the surface element and a similar expression for the thermal energy flux. Now this is the quantity which we're interested in particular in deriving a measure or an estimate for the mass loss rate of a star. Solution of Poisson's equation is now written in terms of an integral phi of x, phi as a function of position x, and t is the integral over density depending on rho and depending on r, and on integrated over r divided by the difference, the modulus of the difference between vectors r and x. The gradient is then taken to be, can be taken as the gradient of 1 over this modulus here, and it's explicitly given in terms of r minus x over r minus x modulus to the power 3. So the energy balance then finally will read as follows. Once we integrate the potential, or once we take an integral over the potential, then we have the change with time of kinetic energy. Thermal energy plus gravitational energy is given by the flux of energy through the surface by either the acoustic flux or the thermal flux. There is now a factor of 1/2 appearing once we consider an internal gravitational potential, and this factor is actually 1 when we have an external potential, once we put our configuration into the potential of an external body. There has to be a difference whether the gravitational field is generated by an external configuration or whether the potential is generated intrinsically by the configuration which we consider. Well, the proof for the factor 1/2 for the internal potential is not quite trivial. Nevertheless, you never find a proof for it in the literature. And actually, when we published this paper, the referee asked us, could you provide a proof for this factor 1/2? And so we added an appendix which includes the proof for factor 1/2 for the internal potential and for factor 1 for the external potential. So if you are not familiar with that, you can go here and take the proof from here. Okay, well, I will not go into the details, but this is the way how to prove in the case of external potential that this can in fact be written. The integral over rho velocity times grad phi is given by the time derivative of rho phi. This gives the factor 1. This is a simple derivation. But if you have an internal potential, then you need to go into the form or the representation of the gravitational potential using the solution. Well, you have to go to this double integral, and the trick here is that you get, once you write down the equation for rho times the velocity times the gradient of the potential, and go in and express the potential in terms of the integral, you get an expression which is asymmetric with respect to the variables x and r. So if you do this straightforward, then you get an expression which is not symmetric with respect to x and r. Well, it should be an expression which is symmetric in x and r. It must be, because nobody tells you that an exchange of or renaming of x and r should change the value of the integral. So you just for the derivation or to get a symmetric form of that, you interchange the x's and the r's. So you replace r by x and x by r, and you obtain an asymmetric version of this integral where r and x is exchanged. But the exchange does not change the value of the integral. So if you take the sum of these two, then they should be equal, and they should be equal to the original value. So you can make, from the consideration that these two integrals should be equal, you can write it as the half of the sum of both. If they are equal, then they are equal to the half of the sum of two. This means this is 1/2, and that's how the factor of 1/2 comes in, is given by now a symmetric form of this integral. And finally, we can then go back and end up with the following form of the rho times u times grad phi, which is then found to be 1/2 d by dt of rho times phi. This is the gravitational energy in terms now for the case of an internal gravitational potential. Now, conservativity requires energy balance intrinsically, and it needs to be satisfied by a numerical scheme. Now, what we are doing, well, it's the same as before. For the velocity, u times du by dt is 1/2 d by dt of 1/2 u squared, and the other differential operators or other differential manipulations you do once you derive the energy equation is that the divergence of pressure times velocity is velocity times the gradient of pressure plus the pressure of divergence of the velocity. Also, this relation to obtain energy conservation, this relation needs to be satisfied also by the difference scheme. It's satisfied by the differential scheme, by the differential operators, but it is not necessarily true for the difference operators. And because we need it for the energy conservation, this differential relation, we need it for the difference scheme as well. So we have to guarantee that this property is also found for the difference schemes. Okay, now different schemes without gravity are available. I already said that for a long time, for almost 40 years, but not with gravity. Okay, we'll do the same as before for the radial case. We define a grid, or we define a grid, and we define cells and nodes. The masses are automatically conserved if we adopt a Lagrangian scheme. The density is simply given by the masses of a cell divided by their volumes, and if we keep the masses of our cells constant, mass is conserved automatically. We don't need to care about mass conservation. So in Lagrangian scheme, and we, apart from the masses of cells within cells, we can define masses of the nodes. This can be done by associating each node, or as distributing the mass of a cell to a same amount to all of its defining nodes, and then collecting for the nodes all the fractions of mass from the different adjacent cells. So then we can also have masses of nodes. So this does not depend on the grid, or whether it's a triangular or it's a cubic grid. So this definition is independent of the size or the form of the grid or the cells you're using. Now integration with respect to density, with respect to the volume times the density, is then simply summing up all the masses which you consider in your consider in your configuration. So integral over dr will be noted by mjr, and integral over dx will be denoted by mix. So integration is simply summing up masses multiplied with certain quantities. Position velocity vectors, again defined on the notes, and for conservativity we already know we have to insert a weight 0.5 for the velocity, so we know how to discretize with respect to time the velocities. And now the question is, well, once we consider the internal potential, we know d by dt of the integral over the volume of 1/2 times rho times phi is the time derivative of the gravitational energy. Well, now we rewrite it in terms, or we write the integration in terms of the summing up over the masses. So these integrals are now written as sum over mjr mix divided by 1 over now the position vectors r and x at the various nodes. So this is the discretized form of this double integral, and now we apply the d by dt. d by dt is then, according to the definition of the time derivative, is minus g halves sum over mj mi rx is 1 over the modulus of the difference between rj and xi at the new time step minus the same value at the old time. This is simply the definition of the time derivative. So this quantity is symmetric with respect to an interchange of r and x. Now, well, so we can rewrite this in terms. Rewrite this term. You can convince yourself that this quantity here, this bracketed quantity, is equal to this rather lengthy expression here. It's simply a simple algebra which needs to be done to verify that this is actually the case. Well, now let's consider this quantity, which is the quantity similar to this above, and permutate the r and x. What we are left with here is the second quantity. So this is equals to the above quantity, and we want to have an asymmetric form of this quantity. Then we do the opposite what we did before for the gravitational potential. Once we derive this factor 1/2, we obtain an asymmetric version, and we take this quantity. We do not have the quantity the factor 1/2, but we express it in terms of an asymmetric quantity. So we follow closely the derivation of the energy conservation law, which we considered before to derive the factor 1/2. Well, and this quantity, which is now obtained by removing this factor 1/2, this has to be, for conservativity, equal to the rho times velocity times the gradient of the potential. Well, this might be written, first of all, in terms of the integral representation of the gravitational potential, and well, this is now to be represented by this quantity. So this means, just for conservativity, we have a special form of we have to discretize the gradient of the potential in this way to obtain conservativity with respect to the gravitational energy. Okay, so this is the form how the gravitational potential has to be represented numerically, and we see it contains not only the values of the radii of the nodes at the old time step, but also that of the new time step. So this scheme is necessarily implicit with respect to time. Well, I don't expect that you have followed this analysis or followed the algebra here in detail. If you are interested, you can try to, or you you have to do these calculations yourself to be convinced that in the whenever we represent the gravitational potential in that way, that we have conservation of energy. That means the conservation, the energy balance is satisfied intrinsically once you adopt this differentiation scheme. You see, you would not have expected, or you would not have guessed this form of the differentiation initially, or without any support. This is cannot be guessed from other points of view. Okay. Well, the nice thing about this formulation of the gravity is that you do not only have energy conservation, but if you ask whether you have angular momentum conservation, then you will find this representation implicitly also, or intrinsically also, guarantees momentum and angular momentum conservation. But the disadvantage, of course, is you ask for conservativity, but the drawback is it has to be implicit with respect to time. You have to solve an implicit equation to simulate the evolution of a three-dimensional configuration. Okay, this is, so to say, I wanted to show this as an outlook what is currently done. We use now this conservative scheme for gravity, and the next step would be to implement this into a code and then to perform three-dimensional calculations, and you are invited to participate in that project. So if you like to construct a 3D code for the simulation of 3D stellar pulsations and instabilities. Well, to close the session and to finish with this lecture, of course, it's always nice to have colorful pictures, and of course, these simulations, CFD is usually an abbreviation for computational fluid and dynamics, but nasty colleagues say always say this is an abbreviation for colored fluid dynamics. And let me present now an example for colored fluid dynamics. This what we no stop. I would like to. Can you stop it again? This is a graphic or a colored animation of the evolution of the instability of a massive star. Now we have color-coded on the upper panel. We have the density, where high densities are yellow and low densities are blue. And more informative is the bottom panel, which shows the density as a function of radius. And what we will see is now what happens once the evolution proceeds. We start from the hydrostatic model, and you see here in the upper panel you see the time in seconds. So this is, if you like, the real simulation of a spherically symmetric star. Of course, let's discuss this here in more detail. This is the run of the density. Well, for this star we have a density inversion here. This, you see, the density increases close to the surface, and we are now starting from the hydrostatic model and looking for the evolution, the time evolution of the density profile. So now we can start the animation. The red line is the photosphere. You see, now we have shock waves forming, and these shock waves move or shift the outer boundary, increases the outer boundary and inflates the star. This is the effect which we have seen. The period of pulsation increases because the star is inflated, mean density goes down. That's what we see here. The star does not, the radius of the star is significantly increasing, and that means density is decreasing and the period increases. Perhaps we can show it once again because it's so nice. Now we have start with the hydrostatic model. This is the linear range, and now we have shock waves which develop. Shock waves coming also from the interior and shift or push the outer boundary to larger radii. So with this movie, I would like to finish. Thank you very much for your attention.